All right, folks, the answer to question 1 is D. And so let's talk through that a little bit. You know that the horizontal speed never changes, so let's just make up a number. Let's say that the horizontal speed is 5 meters per second. So no matter where the projectile is, that is always the same. Okay, and then the vertical speed starts out with some big value and gets smaller. So I'm just making up a number. Let's say that here the vertical speed is 3. You know at the tippy top, Vy is 0. And by symmetry, it's going to regain whatever speed it lost at a rate of 9.8 meters per second. So if these two have the same height, it is now on the way back down going in -3 meters per second. Sorry, the units got mucked up there, but all right. And then the question is about the speed. So whenever they don't reference horizontal and vertical, what they mean is the total. So the total speed is going to be the purple vector, which is the square root of 5 squared plus 3 squared, or the square root of 34. So 5.83 meters per second. And the same thing here. 5.83 meters per second. And the speed here is only 5, because 5 squared plus 0 squared square root is going to give you 5 back. So here and here, they have the same speed, and it's greater than at VQ. All right, number 2, Mr. Jai's testing the Batmobile. So in trial 1, the Joker has a slow speed. In trial 2, it has a faster speed, but the Batmobile is going the same rate. Okay, in trial 2, with a speed of 2 meters per second, it's going to take longer for gravity to take all of that the speed away, and in that same time, the ball is going to go higher, so it has a greater max height. If you wanted to test this, you could plug it in, since we don't care what time that happens. You could plug it into v squared equals v naught squared plus 2a x minus x naught. And to find x, it's really y, but to find the max height. Okay, so A is true. B is also true, because if you have a greater initial speed, it's going to take longer in time for gravity to take that away. You could also prove that by calculating the time each one spent using the velocity function, since we did care about time. C is the tricky one. It's really tempting to say, oh, horizontal doesn't affect vertical, but the whole point of range, the range of a projectile, is affected by both the horizontal and vertical, because remember, the range is Vx times t. So we know that ball number 2 spent more time in the air. That went up. Vx was the same. The Batmobile had the same speed, but if time went up, then the range went up. So C is also true, and I'll erase the diagram and give you a little visual to convince you, because this one tripped me up. All right, so what I drew for you was ball number 1 is in green, and it reaches a peak and comes back down in 5 seconds. I just made those numbers up. That's not the right numbers, but just for visuals. Ball number 2 is launched with a greater speed, so it takes longer to go up. In that time, it's going to go farther, and I ran out of space, so pretend like there's one more of these. It goes up. So the ball number 1 took 3 seconds to reach the peak. Ball number 2 took 4 seconds to reach the peak, and so there should be a 4th picture here. So since it's in the air longer, the Batmobile went 2 more. No, you would have 2 more images of the Batmobile. So it also lands farther down the track. Okay, so this is just a different way of reinforcing the fact that the range of a projectile is affected both by the horizontal speed and the time in the air. That one's kind of tricky. All right, question 3. If the monkey hunter demo were repeated on a planet which the acceleration of gravity was twice that of Earth. So here's the monkey in the tree. Here's the t-shirt cannon. If gravity is stronger, so this is the t-shirt cannon would have this path without gravity, with gravity, let's say here's Earth, and that's when the monkey gets the t-shirt. Different color. On the other planet, if gravity is stronger, it's going to pull it away faster, and the collision would occur lower than before. But one thing that's pretty cool is that whatever time they would collide without gravity, they actually still collide at the same time. But because in that same time, you get gravity pulling you down for free. Like, you don't have to work hard for that. Gravity's doing that for you. So they would collide at the same time. That's kind of tricky. But since gravity's stronger, the collision would happen lower. Okay, I forgot to label A and B. Hopefully you decided A was the first one, B was the second one. Which rocket spends more time in the air? So what determines the time in the air is technically when x equals 0 and y equals 0 when it hits the ground. But since this is symmetric, you can also just say it's going to be double the time at the peak, and because it's a little bit easier to think about. Because at the peak, v equals 0, and on the ground, y equals 0, and that's a quadratic, and that's not. So this is easier to deal with. Okay, so how do you find when v equals 0? You take just the initial y velocity, and you keep subtracting 9.8 from it until you get 0. Okay, so the projectile B had a bigger v naught y. V naught y in the for B is bigger than V naught Y for A. So rocket B absolutely spends more time in the air because it has a bigger initial Y velocity. And 9.8 is the same for both. Okay, question 5. Which is going faster at peak altitude? At peak altitude, each projectile only has its horizontal velocity. But look at that. Projectile B has a greater horizontal velocity. So projectile B is going faster at the peak. Okay, number 6, a little bit tricky. So Miss Groppe is setting up a shoot and shoot demo. She's going to launch ball A, and it goes forward and falls. She wants to launch a second ball at point B. So the point of this one is that B is lower. So it is going to have less time in the air. So if you want it to have actually a larger range than A, then you might think, well, that can't happen because it's going to hit the ground too soon. But if it's covering ground fast enough, it will cover more ground in less time. So we don't, the reason I think I said which could be true, we don't know without doing the numbers, we don't know the heights. But what you could do is, and the answer may not be 10 meters per second, but as if there's some speed at which, you launch B fast enough to make up for the fact that it's going to have less time in the air. Because again, the range is your horizontal speed times the time. This is going to have less time, so it better have more speed. Okay, so 10 is bigger than 5. So that is going to work. Vector number 2, by launching it up, you're going to gain some time in the air because gravity is going to have to bring it to rest and then pull it back down. So again, we don't know exactly what these numbers are, but there's some value at which this additional upward velocity will give us some time. So it's okay that my forward velocity is the same. By going up first, I might spend as much time in the air as this ball, and then cover the same ground. Okay, I know this is a little bit longer distance, but I think I just drew it like that so that you could see what's going on. Okay, so you could also make up for the shorter distance by launching it up. But this is absolutely not going to work because I'm launching it down, and that means I'm going to help it hit the ground sooner by sending it towards the ground, and then gravity is going to help me out even more. And so there's no way I'm going to fall way short because I'm only going forward as fast as A, but I'm going to hit the ground much too soon. Okay, so vector 3 is not an option. Okay, hope that was helpful for you to think about how to do the conceptual problems. Don't forget there are also calculation problems. And good luck, and I'll see you in class.